Hello, everyone. My name is Natalie, and I am here with Katie, and we are presenting our senior design project and titled "A Handheld Device to Quantify Facial Asymmetry Through Computer Vision." And just to give a little background on this device, so facial drooping is one of the earliest signs of people with stroke or people with Bell palsy and or anyone with at risk of stroke for the first time. And it can be difficult to detect some even the subtle changes within facial asymmetry. And let's say we have a patient coming into the hospital and they're showing all these signs of a stroke. And one doctor can have a different opinion as to whether this person is having a stroke versus another doctor, let's say. And so our device can detect the severity or depth of asymmetry within our faces, and um and it can help reduce that subjectivity um and increase on having that objectivity. And the way that we're doing that is to help um uh guide like therapy or monitor recovery over time of people with this specific issue. And so our project aims to develop an asymmetry index to establish a score range using a portable self-contained system that quantifies facial asymmetry in droop. And these scores with the various quantification codes from like computer vision and Python is with this consistency from previous methods would help us in obtaining these normal population values. And just to give you a little more background on stroke patients, they can have different kinds of stroke. Some can be in the lower part of their face, which and some of it could be from the upper part of the face, and it can really differentiate in certain parts of the brain as shown in figure 2. And to give you a little screenshot of our device is shown in figure 1 with our first iteration versus our most recent iteration, which I'll have Katie explain more about in the experimental setup and test plan.
Okay, so for our experimental setup, we have a couple of requirements here on the left. We have our functional and physical requirements and our constraints. The functional requirements is basically what we want our device, how you want it to, I guess, well, function, right? So objective and accurate and reliable, be able to integrate well into clinical workflow, and then just give us consistent results across a bunch of different skin types and lighting conditions. For our physical requirements, we want this device to be around 3 kilograms or less, just basically being able to be held up with one hand. Last a day without charging. We don't want it to be reliable on charge too much. And then again, just safe in the clinical environment. For our constraints, our budget is $1,000. We've used about half of that. And then for our software, we're using Python, and our housing, we are using a 3D printing. We want it to be secure. So figure 3 and figure 4 shows kind of the bare bones of what our prototype is. It basically contains a Raspberry Pi, our OT-like camera, and a power supply, which goes through the Raspberry Pi to be able to power our camera, the Pi itself, and then be able to display it on the display. Figure 4 shows that from a bird's eye view. You have the power supply on the left, the Pi, and the display is a little hard to see, but it's there at the front, and then the camera in the back with all the kind of cables in the middle there. And then for our how exactly we are going to do our asymmetry values, we gathered a handful of research papers. We found a couple that worked for us. We need to first find out what landmarks were beneficial because there are hundreds of landmarks in the face. Figure 5 shows the ones that we've chosen with the help of our clinical mentor. These are the kind of the ones that are just most important to us right now. And then figure 6 shows our official final formula that our code currently works on. So from the midline on figure 5, that black line down the middle, that is our reference point. Every landmark on the left and the right of the face, there is a distance, and that distance value gets plugged into that formula, and the formula basically calculates the difference between the distances from the left of the face to the right of the face. And then right now our Python code runs on 3 major libraries: OpenCV, MediaPipe, and NumPy. Each of them kind of target a different thing. Like NumPy is what calculates our formula. MediaPipe is what uses to calculate those landmarks or to identify those landmarks. And then figure 7 shows how our code is running. This is like really early on of how our code ran. And you can see on the left, it's a little bit asymmetrical, and on the right, it shows a more balanced face. And then for results, how our code runs is the smaller the number, the closer the number is to 0, the more symmetrical it is. So right here on face 1, we see on the left, he has a little bit of an asymmetrical face. And these are Bell's palsy patients who have undergone treatment. So on the right, you can see he's undergone some treatment, and his face is now considered balanced. But then face 2, what we want to be able to kind of point out is his before and after are very similar. It's something that it could be very subtle. So as to the naked eye, we can't really tell that he has some asymmetry, or he'd even gotten better in the first place. But with straight number values, objective number values, we're able to tell that, oh yeah, his symmetry got a little bit better.
So in conclusion, our results are calculated from the code to detect the asymmetry and give verdict on the location of the asymmetry. And as Kitty mentioned, we're able to detect the subtle changes, but building upon the foundation moving forward, future improvements will be focusing more on the sensitivity and redefining the landmark accuracy. So thank you for your time. Next, we will have Anthony demonstrating our device and how it works, and having one of our friends being our guinea pig uh, in our demonstration. So thank you for your time. Moving on to Anthony.
Ready? Okay, so here we have a balanced face, and we see the asymmetrical indexes are pretty low. Now I'm gonna ask Jerome to give us a lower asymmetry, so give us a droop effect. We get that lower symmetry is detected, and we see our ASI lower is a higher number because we have that distance formula that's a little wonky. Now, Jerome, let's try to see if we can do some eyes drooping. All right, maybe a little scrunch. Let's get a little scrunch. So that one's not as sensitive, so we're still troubleshooting that. But with the lower asymmetry, we're able to get dictate and pick up those asymmetrical indexes.